Welcome to the fourth video in the series called Video Standards, Signals, Formats, and Interfaces. Except for the artificial images created by computer animation programs, any video image originates from an optical image. Today you will learn more about the magic transformation of spatial light distribution into video signals. The magic device is called the video camera. The important parameter of light to signal transformation is called a conversion gain. It's the amount of incoming light required to get a particular video signal level at the camera's output. This gain depends on a variety of parameters which are better understood if we look at two big building blocks present in any video camera. The optoelectronic block, starting at the entrance pupil of the camera lens, producing a triplet of so-called raw video signals, red, green, and blue, and a sophisticated video signal processor, which converts this raw video into the final color image. Standards define only some details of this process. Most importantly, they specify the generic parameter, optoelectronic transform function, or OETF. Standards also define the reference black and reference white levels. To make good video images, a camera should be controlled, manually, automatically, or semi-automatically. Human factors and wrong control values are the most common causes of substandard video images. By knowing the standards-defined parameters, such as system primaries and light source color temperatures, we can estimate the required range of RGB gain settings. These three images illustrate three stages of video processing. Within the sequence of image color corrections, black levels should be balanced first. Otherwise, any change in RGB gains meant to adjust white levels will require readjustment of black balance offsets. The choice of color correction matrix coefficients plays a pivotal role in color rendition optimization. Imagers, meaning camera chips, cannot produce negative signals. To produce good colors, the camera's R, G, and B channels' spectral responses must have negative lobes. A matrix color corrector adds and subtracts the color signals of the adjacent channels, so the resulting mix is closer to the ideal curves. Historically, the purpose of camera gamma correction was to precompensate for the nonlinearity of a typical display and its electro-optical transfer function, or EOTF. Gamma is a Greek letter commonly used to define a more or less accurate approximation of the EOTF by a power function. Standards set the camera gamma value to equal 0.45, but real gamma correctors use variable, adaptive, and much more sophisticated curves. So we should remember that the OETF functions defined in the standards are just a guidance. The slope in gain of the theoretical display EOTF at the reference black point is 0. To compensate for this gain, the inverse OETF slope must be equal to 1 over 0, in other words, infinity. The solution is a standards-defined hybrid curve consisting of a linear segment with a fixed slope for the lowest input levels and slightly modified original gamma curve for all other levels. Partial replacement of the ideal power function by a linear segment has one unpleasant side effect. Dark levels, meaning deep shadows, are not fully compensated, so the display EOTF will compress them. One possible solution is to increase the linear segment slope and thereby reducing the unwanted compression of dark gradations. This mode is often called black stretch. For sRGB, that's the video color space used by computers and the World Wide Web, the 4.5 slope is increased to nearly 13. Some broadcast cameras also use this trick, so to speak, breaking the law. Cameras seldom meet parameters very close to the nominal target values set by standards. With few exceptions, the standards don't specify tolerances for light to signal conversion parameters. However, there are tools and methods suitable for a video camera's performance in subjective estimation and objective measurement. VideoQ presents here some of these tools. This video was prepared for you by a team of experts. Produced and narrated by Joseph Mark, a member of SMPTE's HDR committee. Written by Dr. Victor Steinberg, co-founder and president of VideoQ, technical awards winner and author of the Video Standards book. Conceived by Roderick Snell, co-founder of Snell & Wilcox and winner of several technical Emmys and Queen's Awards. Technical consulting by Maxim Levkov, author of the Video Encoding Cookbook. This video series is brought to you by VideoQ, and you can download these slides and this video from VideoQ.com. VideoQ makes products and services for all sorts of video and audio processing and quality assurance. Based in Silicon Valley with software developers and distributors in several countries. Thank you for watching.